Hi everyone. This is Krish Patel, a third-year VLSI engineering student. In today's lecture, we will be discussing a fundamental component of modern digital systems, the DSP processor, or digital signal processing processor. This is a highly specialized processor that plays a crucial role in many real-time applications such as audio processing, telecommunications, medical devices, and more. Let us begin with a basic understanding of what digital signal processing actually means. Digital signal processing, abbreviated as DSP, refers to the mathematical manipulation of an information signal to modify or improve it in some way. The signals may represent audio, video, temperature, pressure, or any physical quantity that can vary with time. Typically, these signals exist in analog form and are converted into digital form using an analog-to-digital converter, or ADC. Once converted, the digital signal can be processed using various algorithms. Can anyone tell me why we prefer digital processing over analog? Correct. Digital processing provides better accuracy, flexibility, and resistance to noise. Some common DSP operations include filtering, compression, and feature extraction. Now that we understand what DSP is, let us look at the processor designed specifically to perform these tasks, the DSP processor. A DSP processor is a microprocessor specifically designed to perform the intensive mathematical operations required in signal processing applications and to do so in real time. While general-purpose processors or microcontrollers can perform similar operations, they are not optimized for repetitive mathematical computations and real-time constraints. Can someone explain what real-time processing means? Exactly. Real-time processing refers to the ability to process data and produce output almost instantaneously within a defined time constraint. DSP processors have several architectural features that distinguish them from general-purpose processors. Let's go through the key features. MAC unit, multiply and accumulate. This allows the processor to perform multiply and accumulate operations in a single cycle crucial for filters, FFTs, and other DSP algorithms. Harvard architecture. In this architecture, the processor uses separate memory buses for data and instructions, enabling faster access and better throughput. Pipelining. This technique allows the execution of multiple instructions simultaneously by breaking them into different stages. Circular buffer support. Useful for implementing delay lines in filters without the overhead of manual indexing. Low power consumption. Many DSPs are designed with low power modes, making them ideal for portable and battery-operated devices. A quick question: what does the MAC unit help us achieve? Yes, it significantly speeds up operations that are central to DSP tasks. Let us now discuss some of the key application areas of DSP processors. Audio processing, noise cancellation, equalization, and audio compression, example, MP3 encoding. Image processing, enhancing image quality, object detection, facial recognition. Telecommunications, modulation, demodulation, error correction. Biomedical engineering, ECG, EEG signal filtering and interpretation. Consumer electronics, mobile phones, smart speakers, hearing aids. Automotive systems, advanced driver assistance systems, ADAS, sensor fusion. Can anyone name a real-world device that you think uses DSP? Mobile phone, hearing aids, smart TVs. Yes, all of those are valid examples. Several processor families are widely used in industry for DSP applications. Some of the prominent ones include Texas Instruments, TI, TMS320C6000 and C2000 series. Analog devices, Shark and Blackfin processors. ARM Cortex-M series. Some variants include DSP extensions using CMSI's DSP libraries. Have any of you worked with ARM Cortex-M microcontrollers during lab sessions? Good. You should know that certain ARM cores include SIMD and DSP instructions that can perform signal processing efficiently. Let me now give you a simplified example to help you visualize how a DSP processor functions in practice. Consider a scenario where you are on a phone call in a noisy environment. The microphone captures your voice along with background noise. The DSP processor runs a digital filtering algorithm, for example, a low-pass or band-stop filter, in real time, allowing only the desired frequency components, your voice, to pass through. The result is a clearer voice signal transmitted to the other end of the call. Now, what do you think would happen if we tried to do the same task on a basic 8-bit microcontroller? Delay, dropped signals. Correct. It may not be able to process the signal in real time, resulting in poor audio quality or delays. To summarize today's lecture, digital signal processing involves mathematical manipulation of real-world signals. DSP processors are specialized hardware units designed for fast, real-time processing. They include features like MAC units, Harvard architecture, and pipelining. Applications range across audio, video, biomedical, telecom, and automotive systems. Popular DSP processors include TI's TMS-320 series, analog devices Shark, and ARM Cortex-M with DSP support. In the next session, we will study the internal architecture of a typical DSP processor and understand how instruction execution is optimized for signal processing tasks. Please revise today's concepts thoroughly and come prepared with questions. Thank you.